Hi again. So, where we are at? We are going to continue with indeterminate trusses, but this time we're going to use the second approach. And the second approach is, who am I to say that the diagonals cannot resist compression? Diagonals are strong, strength. They have sufficient power to resist compression. And not only that, they're going to resist equally tension and compression because I made them thick, I made them strong, I made them eat protein every day and exercise. So, I mean, kidding apart, that's what's going to happen, basically. We already calculated this in the previous video that we did with the first approach. We came here and we can calculate the reactions, the external reactions. That's the first step, and verify if this is statically determinate or indeterminate. That's the second step, degrees of indeterminacy, and depending on the degrees of the indeterminacy, then we have to start messing up with the bars. What were the values here? The values were 10 and 8, 10 and 8. So this is 10 and this is 8 here. And this was 0. In the other case, we say, oh, tension, compression, whatever variation, and then the panel and the shear panel and crazy stuff to me. Now, in this case, we said, okay, I know that this is in tension. Why? Because I explained you why in the previous video, right? And I know this is in compression. And once again, this is tension, this is compression, and same thing happens here. So if I know this is in tension and this is in compression, and I know they are equally resisting the tension and the compression, when I make a cut here, instead of calling this FB and AE, instead of me doing that, and I don't want to go into the panel thing, shear panel for the trusses, etc., etc., etc. Once you're doing that cut, and this is FE, and this is AB, tension, compression, yes, and this originally is called FB. And this originally is called AE. Once again, you have the 3, 4, 5 triangle, 3, 4, 5 triangle, 3, 3, 4, 5 triangle. But if these two are the same, as I am claiming, I made them strong enough to be the same, then instead of me saying, in this case the triangle is a little bit different, right? But it's the same, 3, 4, 5. Instead of me calling this FB or AE, I'm going to call them just F. That's it. And this is 8. If I do that, I just come and say summation of forces in Y equals 0. And if I go summation of forces in Y equals 0, what do you get? You get 8 minus 6. And then you have this one, right? This is minus, I'm not going to say AE, I'm going to say F multiplied by 3/5. And here I'm going to say minus, not FB, but F again, multiplied by 3/5. And that's going to be 0. So when you solve for here, you have the F is going to be equal to 8 minus 6 is 2 to 10, 10 divided by 10, right? 10 divided by 3, 1.60 something, 1.67. We'll do it again. I think it's 1.60. Again with the calculator. Okay, 2. Then this is gonna be 2. Cancel each other out. 5/3. Yeah, what I'm saying. 5/3 is 1. 5/3 is 1.67. 1.67. 1.66. 1.6 kilonewton. That's the value of F. And now we have this value. And now we have this value. We can come here and do the same approach if you want to. And you can say, oh, this here is coming here. This here is coming here. So the total of, I'm calling this, I don't know, F2, both of these forces if I want to. and then I do the same thing. I say 10 minus 8 minus 3/5 f2 minus 3/5 f2. Calculate f2, and now I already calculated these two diagonals and these two diagonals here. Problem is solved, because I can come here and do summation of forces in x, y, etc., etc., etc. So I don't want to go and solve the whole problem, but once I'm confident that once you get the value for that force, you already know the rest, right? So the rest is just plain and simple joint or section analysis. The important part is both diagonals, I'm assuming they resist the same. And once again, the assumption comes, it's an assumption, period. Who is going to tell me which one of the methods is better? I don't know. Now, compare both methods. If you compare the previous method, in this case, the force FB and AE was 1.6. In this case, the force FB was 3.3. But the other force was 0. So still the summation of both is going to provide me with the compressive, with the stress, necessary stress, the needed stress to absorb that extra vertical part. I don't know if these are hot roll members, angles, and you see the sections that they are stiff. No, they have to be slender, but they have an important area, let's say like that. Then this approach, it makes more sense than the other approach. But if the diagonals are really slender, then the first approach is the one that makes more sense. At the end, everything is approximated. I'm gonna solve some videos. I'm gonna publish and post some videos later on from the real methods that we use in order to solve trusses and not this approximation. But for now, this is what it is. See you next time, guys. Stay safe. Arrivederci, Roma.